And welcome to the Unbalanced Forces .1. This is our first video of this unit. There is a few, I think 3 mops to do when you're done this, and there's a few your turn pieces of this video. Let's get started. Let's just compare what we mean by balanced forces versus unbalanced forces. And I think it's always helpful to have a number of different ways to represent things. So I'm going to go with you through this chart and we're going to fill it out and we're going to compare balanced forces versus unbalanced forces. So the first one I have is I have a question mark constant velocity. Under balanced forces we do have a constant velocity check. So that could look like not moving would be an example. If something's not moving and it stays not moving. Or another way of talking, we could have constant velocity where it's moving but it's going to stay the same. So, moving but same speed and direction, maybe we could say here. Same speed plus direction. How about for unbalanced? So is it going at constant velocity? No, it's not going at a constant velocity. So another way of saying that is it is accelerating. So we could go a changing speed, or we could actually even also have a changing direction. What would force diagrams look like for balanced forces? So for balanced forces, well, we could have up and down like this. We could have 4 directions. We could even have something at an angle like this with some other arrows. Now, it's a tough one to prove that that one is at constant velocity until we actually figure out these components. And then you could say this component was the same as this one, and this component was the same as that down arrow. So that you could demonstrate was going at a balanced forces. So that's what it would look like. By the way, in all of them, we don't know which way it's moving. This could be our old hovercraft that could be moving left or right. For all of them, balanced forces doesn't mean that it's not moving. It just means however it's moving, it's staying the same. For unbalanced forces, just so that the arrows don't add up to 0. So there'd be an example. So here's the classic example of that arrow going downwards of a projectile, of something that's just falling or sailing through the air. And again, this could be in the middle of on its way up. It could be at its highest point. It could be on its way down. So when you're looking at that one force going downwards, you don't even know which direction it's going. You just know that if it's not balanced, if it's unbalanced, then it is accelerating. How about for motion maps? Well, motion maps, here would be an example of something going at a constant velocity. And remember, we draw these velocity vectors about halfway to the next dot. So there we can see these velocity arrows are about the same length. If something's motionless, we should just draw the dots kind of over top of each other. So those are 2 examples of constant velocity. For unbalanced forces, well, there's many different ways we could draw it. How about we draw dots getting farther apart? So again, here's my velocities. Oh, maybe a little too far there. Something like that. So here's our velocity vectors. You can see the velocity is increasing. What does the velocity time graph look like for balanced forces? Well, if I draw a VT graph, here's for my example A, it would look like this. There was going at some constant positive velocity. For B, it's going 0, so it would actually be here. I'll do a different line here. So for B, it would be just going a constant 0. So what's the takeaway from this? What's in common here? These are horizontal, because the velocity is not changing, so that's why it would be horizontal. For the unbalanced forces, if I just use up my example from above, I see that it would kind of look like this. So here, not horizontal. So it would have some type of a slope. And by the way, just to remember that the slope of this is equal to acceleration. So it has some acceleration, some slope that's not 0. Okay, so another way of writing this, slope is not equal to 0. Could be uphill, could be downhill. Our position time graphs. So if it's horizontal motion, I often put an X for my horizontal position, X position. So what would that look like? Well, for A, for an object that was moving to the right at a constant velocity, it would be, well, it doesn't have to start at the origin. Maybe I'll have it start someplace else, but it has a straight line looks like this. For B, I'll do it in red. That one was the object that was not changing its position, so wherever it started, that's where it was continuing. So that would be an example. So what can we say about those? If it's going at a constant velocity, it's going to be a straight line. If it is unbalanced forces, which means it's accelerating, then we're going to have a curve. Changing slope, changing velocity. What about acceleration? Well, if it's, here's the takeaway here, if it's balanced, the acceleration is equal to 0. And here, if it's not balanced, the acceleration is not equal to 0. And how does this work? The acceleration is going to be equal to whatever the net force is, and F net is equal to the sum of the forces. So in other words, here F net is equal to 0 if something's balanced. That means it all adds up to 0. And here F net is not equal to 0. Acceleration is going to be equal to F net divided by the mass. And just a couple things to note about this. The direction of the acceleration and the direction of F net, same direction. So just looking at this one, F net is to the right, it's going to be accelerating to the right. Looking for my projectile, F net is downwards, it's going to be accelerating downwards. Okay, let's take a look at the next page. A few examples, I'll work with you. And it says here, how is this object moving? How about, how's object A moving? Let's look at object A for a second. So, well, it's accelerating to the left, we know that. It could be an example where it starts here and speeds up to the left, right? Could look like that, in which case it's moving this direction and it's accelerating. That's what it could look like speeding up. Here, I'll draw a couple velocity, right, ones. But let's say if it was moving, if it starts moving the other direction, it could be, moving in the other direction, slowing down. In both cases, it would be accelerating to the left. Here I'll say this one would be accelerating to the left. In this one, the velocity was to the right, but it was accelerating to the left. So it could be moving left and speeding up, or it could have been moving right and slowing down. And in fact, for all of these, how are any of them, I guess the answer is we don't know. Okay, so forces tell you about acceleration. Not current velocity, not velocity. So in other words, in each of those you can tell me which way they're going to be accelerating. This one's going to be accelerating to the left. This one's going to be accelerating to the left. This one will be accelerating to the right. This one will be accelerating to the right. This one will be acceleration equals 0 because they're balanced. But in none of them do we know which way it's moving. So here it says draw a possible motion map for A. Well, I guess I did it already. So that's over there. So I did two possible. motion maps for A. So the one was moving left and speeding up, and the other one was moving right and slowing down. Looking at number 3, it says a skydiver pulls the cord on his parachute and the forces acting are shown. What will happen during the next few seconds? Well, okay, so is it balanced? No, not really. So I would say in this case, F net is going to be up by 1,000 newtons. So, well, which way is it moving? And how will that change? Well, skydiving usually means that we're falling, so the motion is downwards. And so if F net is up, that also means that my acceleration is going to be upwards. So if it's moving downwards and accelerating upwards, this means it's going to be slowing down. Or if I put this into motion map dots, the dots are going to be starting to get a little bit closer together like this. It's going to start slowing down. Okay. By the way, an interesting result of this, if it's slowing down, this would mean that the air resistance actually depends on how fast you're falling. As you start falling at a slower rate, this value of the force of the air pushing up into the parachute is going to come down a little bit. So eventually what will happen, so I'll say in a few seconds, what might happen is that you slow down, and as a result, the new free body diagram, force of gravity is still going to be the same. But a little bit later, perhaps the air resistance has reduced to 1,000 newtons. So a little bit later on, you might get a situation where now F net is equal to 0, or they're balanced. And so at this point, we're going to get constant velocity. And what would this new diagram look like? Well, now at its slower rate, it's going to be falling at a constant velocity. So when you first pull the parachute, you're going fast. And when you pull the parachute, you're going to have a force air upwards that's larger than the force of gravity downwards, which causes you to accelerate upwards and slow down. But then later on, as you slow down, eventually the force air up and the force of gravity down are going to be the same, in which case you're going to be going at a constant velocity. By the way, there is a term for this for falling objects. Once they reach that constant velocity, we call this terminal velocity. Not exactly part of this lesson, but it does come up later in our course. So the terminal velocity is when you have a falling object which eventually reaches a state where the air resistance up and the force of gravity down are the same, so it doesn't speed up or slow down, and it stays at that velocity for the remainder until it hits the ground, really. Okay, example number 4 says a 5 kilogram object is moving to the right at 10 meters per second. What would that look like? So it's moving to the right at 10 meters per second. So, it's going along 10 meters per second like this. There we go, and this is velocity the whole time is equal to 10 meters per second. It doesn't say it's speeding up or slowing down, it's just going 10 meters per second. It says calculate the rightward force required to keep the object moving at 10 meters per second. Well, if it's continued to go, the forces are balanced because it's not accelerating, constant velocity. So you don't really need a rightward force, okay? No force needed. In fact, the free body diagram for this might be like our hovercraft, where you could have a normal force and a force of gravity. It could look like this, and it could be moving to the right. Once it's already moving to the right, you do not need any force to keep it moving. That's just what objects do. That's Newton's first law. Okay, so here's a your turn. I would like you to try this on your own, and maybe what I'll do is on a second video, you can click on it and find out what the answers are just to check your work. Tell you what, I'll start off number 2 for you here. It says Renata oil, or run out of oil, is having car problems. She's notorious for the trail of oil drops that she leaves on the streets of Glenview. Observe the following oil traces and indicate whether Renata's car is being acted upon by an unbalanced force. Give a reason for your answer. So looking at the oil drops, you see that the spaces are getting farther apart. So I'm going to say that must be an unbalanced force. So I'm going to say yes, unbalanced force. And the reason I'm going to put is, maybe I'll say changing velocity. So I think you're going to see if it's changing velocity, you're going to say yes, an unbalanced force. If it's constant velocity, you're going to say no. Is there anything else crazy in here that I need to help you with? I don't think so. So the your turn starts at 1, 2, 3, 4, and then actually 5. So go to question number 5 now, and then when you're done, you can check next video for the answers. All right. I will see you soon. Bye-bye.